The normal distribution shows up in statistics very often because of something called the central limit theorem. But why does it have this specific function? Why not some other? There are plenty of graphs which have a similar shape, bulging in the middle and dropping at the sides. What's so special about this specific curve? And where did it even come from in the first place? In this video, I'm going to show you historically the question which birthed the normal distribution and where it even came from in the first place. Our story begins in 1733 with French mathematician Abraham de Moivre. De Moivre was studying binomial expressions like a plus b to the n. Specifically, he was studying the binomial coefficients. He wanted to know if there was a way to approximate these coefficients in cases where calculations would be too tedious to perform by hand. This is particularly useful to probability theory because one of the simplest distributions in statistics uses the binomial coefficients, the aptly named binomial distribution. Suppose I have a coin and the probability of heads is p. If I flip the coin n times, the probability we get a certain number of heads, say x, can be found by using a binomial distribution. This distribution directly involves these binomial coefficients, making it clear how de Moivre's approximation will be useful. First, I want to make sure that we're on exactly the same page here. Suppose the probability of heads is 0.6, that's 60%, and I flip the coin 15 times. We can get anywhere between 0 and 15 heads. Here, I'll let the computer run 250 trials of this experiment, and we can see what happens. We get this kind of shape which bulges in the middle and drops down at the sides. Our goal today is to determine the precise shape that this curve approaches. The binomial coefficients which de Moivre was trying to approximate involve a lot of factorials. Luckily, de Moivre had come up with a factorial approximation 3 years previously in 1730. This is how he did it. N factorial is defined by multiplying many things together. Addition is usually easier to work with than multiplication, and we can turn multiplication into addition by using logarithms. De Moivre realized that this sum could be approximated by an integral. The integral is precisely the red area. We can approximate this red area by using trapeziums. The error between the trapeziums and the red area is worst for the first few trapeziums, and even if we make n larger, this error isn't going to shrink. But the error from the new trapeziums will be less. To account for this constant error for the first few trapeziums, we'll add a constant. When you calculate the areas of these trapeziums and add them together, you get this nice formula called the trapezium rule. To account for the unshrinking error in the first few terms, we add a constant k. We don't know yet what this constant is, and neither did de Moivre. This is almost identical to what we have at the top. If we subtract a half log n and a half log 1, which is just 0, from both sides, they become the same thing. We can evaluate this integral exactly by using integration by parts. Finally, we can exponentiate both sides to get an approximation for n factorial. E to the k plus 1 is just some constant, so we'll relabel it as c. De Moivre was not able to figure out the value of c, but that same year in 1730, Stirling figured it out to be the square root of 2 pi, which is why today we call this Stirling's approximation. Stirling did this by using numerical approximations with large values of n, but we'll see a more insightful reason later as to why c takes on this surprising value. For now, we'll pretend that it's unknown. By the way, if you want to learn more maths from me, click that top link in the description for my real analysis course. I'm planning on adding other courses in the future like probability, calculus, and linear algebra, so check it out if you're interested. We're now ready to use de Moivre's approximation on the probability for a binomial distribution. For the sake of being concise, we'll let q equal 1 minus p. Our approximation is best for large values of n, but even for small values it's still a very good approximation. We can apply this approximation to all the factorials in our probability function, and luckily we can simplify this considerably. Now this expression we've ended up with involves a lot of powers and things multiplied together, and this would likely be much easier to deal with if we took logs on both sides. We mostly care about the shape of the curve near the peak, that is where x is close to np, and when this is the case, np over x and nq over n minus x are each close to 1. This then allows us to approximate these two logarithms using the Taylor series approximation, which is a good approximation when x is close to 1. Applying this approximation and simplifying, it's at this point again that de Moivre used the assumption that x is close to np, and finally we can now exponentiate both sides. You might notice that np is the expected value of the binomial distribution and npq is the variance. We can now clearly see where the normal distribution comes from, but we still need to determine the value of this constant c. Stirling, as I mentioned before, did this by numerical approximation, but we can do something a little bit more insightful. First, consider the simplest case, where the expected value mu is 0 and the standard deviation sigma is 1. Since probabilities must add to 1, we can integrate this from negative infinity to infinity and set it equal to 1. This integral is actually very difficult, but it can be done with a clever trick. There are already many videos on YouTube on this exact integral, called the Gaussian integral, and it evaluates to the square root of 2 pi. I won't go into the details here as there are already so many videos which do this, but the details are on screen if you want to read them. Don't forget to click that top link in the description. Hopefully this video has given you a better understanding as to where the normal distribution originally came from. It shows up in many more general situations because of something called the central limit theorem, which I may look at in future videos. I hope to see you there. Click that link. See you next time. Bye.